Okay, let's work on problem E from these practice problems. Again, very similar to C and D, same type of starting material, different reagents. So using Cl2 and this alcohol isopropanol. First thing we want to do is number our carbons 1 and 2. Got a Cl2, so let's draw Cl2 a little differently. Let's draw it like this so we can show these arrows moving. So our pi bond is our nucleophile. It attacks the chlorine. Chlorine-chlorine bond breaks. Then at the same time, one of these lone pairs on the chlorine comes back and attacks carbon 2. So we end up getting a chloronium ion. And I think the best way to draw them is like this. Cl has a plus charge. This is carbon 1. This is carbon 2. We also generated Cl minus. Now, because in the bottom part of the arrow indicates solvent's in a much higher abundance than Cl minus. The nucleophile in the second step is actually going to be the alcohol. And then we have a choice, attack carbon 1 or carbon 2. We attack carbon 1 because it's more substituted, so it has more stabilizing effects because of hyperconjugation, so it's more plus delta plus charge, so that's the one we attack. And we always attack it in a backside attack fashion, so a trans fashion. So we attack carbon 1, we break the carbon-chlorine bond. Chlorine's still up. The alcohol attacked is here. There's a plus charge on the oxygen. Alright, and then the second step, the H plus leaves. We get our final product. Where the Cl and what was the alcohol are trans to each other. We also get the enantiomer as well. Because in the initial step, when the chloronium ion forms, we also could have had it attack on the bottom side too. We always love it attack too. When we regenerate H+, so this is acid catalyzed, we always get the enantiomers, so always have a trans product with chloronium, with bromonium or chlorine, Cl2, Br2. We always get racemic mixtures if we form an asymmetric center. We always got to be careful about what is the solvent. If we have an alcohol, we end up with an ether. If we have water, we end up with an alcohol. Now for F, we have a similar type of problem as before. But now instead, we have Br2 with no solvent. So our electrophile and nucleophile. Nucleophile is the pi bond. It attacks the bromine. And then a lone pair on the bromine comes back and attacks the pi bond. So we number our carbons 1 and 2. And I like to draw them like this. I put the Br there. Put a plus charge. Put a Br minus here. Now to decide what goes where, here, I see in carbon 1, this methyl here was always trans to this methyl here. So if this is carbon 1, and this is carbon 2, that means this methyl must be trans to this methyl. If there was an H on carbon 2, and it was opposite this ethyl group, I make sure they're opposite in this bromonium ion. Now again, we got to decide which carbon to attack, which one's the most delta plus, most likely to be attacked, and it's carbon 1 because it's the most substituted, and it attacks in the back side. So there's your Br, another Br, methyl, methyl, and H. Now you also will make the enantiomer as well. Right? So these BR additions are always trans. We get racemic mixtures if we form asymmetric centers, which basically is saying the enantiomer is there. Also be careful, right? We always want to attack the most substituted carbon. Alright. Problem G, we got an added little wrinkle here. We have a molecule that already has a stereocenter in it. H plus. That's an H. So in this case, everything's the same. We have a strong acid, pi bonds the nucleophile, attacks the H plus. Right? We form, number our carbons 1 and 2. We form the carbocation on carbon 1 because it's the most substituted, so it can stabilize the charge the best. Right? Because of hyperconjugation. 1 and 2. Now we always start out with one enantiomer though. Right? So now we also made water in this process. Second step, water is going to attack, and there's no preference for it to attack top or bottom. So you're going to get a racemic mixture attacking there. So you're going to get both this and you're going to get equally as likely to get this. Now the interesting part here is, what is the relationship between these two things? Right, so if we lose the H in both, the two final products we get are alcohols, but their relationship, they're not enantiomers to each other. What they are to each other is diastereomers. Right? When you have one stereocenter that stays the same, and the other one, at least one more that's different, you have diastereomers. So the relationship to the products equally is likely to form their diastereomers. Alright, let's work on H. So H again gives us a product first and asks us to try to figure out where did that product come from. Alright, so it's a BH3. And so let's draw this product out. OH. Okay. So we got to decide where did this product come from. So we know it had to come from an alkene, right? Because that's what we've been talking about. So we know it's an alkene. We know BH3 goes on the likely on the less substituted carbon. So we have to envision where this alkene came from. First thing, let's number these carbons: 1, 2, 3, and 4, and 5. So the only place the alkene, if there was an alkene, had to come from would be between carbon 3 and 4, right? Because the functional group ended there, and we know BH3 adds an OH and an H. So the starting material alkene would have to be this, where this is carbon 1, 2, 3, 4, and 5, and the alkene could have been between carbon 2 and 3 as well.